Welcome. Today's topic, why LLM models hallucinate and how to fix it. We are going to look closely at why these systems invent facts, and more importantly, how to build the architecture required to stop them. As this diagram illustrates, an LLM processing a prompt faces a choice between factual accuracy and statistical plausibility. Hallucinations occur when the model outputs a confident, fluent, and grammatically correct response that bypasses the facts entirely and relies on what simply looks correct. This manifests in several distinct ways. The first is fabricating facts. A model might invent historical events, generate fake news articles, or cite non-existent academic papers. Second, models produce incorrect information. They will provide wrong dates, skewed financial figures, or inaccurate technical details while maintaining an authoritative tone. They will also generate context-conflicting outputs, text that directly contradicts a source document you just provided in the prompt. Finally, there's forced hallucination. This occurs when a user pushes a model to answer a query falling entirely outside its training data. Hallucination is the predictable outcome of training a system to prioritize conversational helpfulness over factual truth. The root of this behavior lies in how models are trained. Historical reward mechanisms, using binary right or wrong evaluations, penalized models for saying, "I don't know." Like a student on a test, the model learned to maximize its score by guessing when uncertain. Because large language models predict text based on statistical likelihood, if a fabricated statement sounds more plausible within the immediate context than admitting ignorance, the model will output the fabrication. Unlike humans, these systems do not possess real-world experiences or a constantly updated internal database to verify the information they generate. Fixing this requires a four-layered defense-in-depth architecture. As we see mapped out on these cards, we will examine grounding through RAG, advanced prompt engineering, model tuning, and finally, verification guardrails. This roadmap combines design time interventions to shape the model's behavior with strict runtime constraints to control its outputs. Product managers cannot rely on a single prompt or a quick configuration tweak. Stopping hallucinations demands this comprehensive, multi-layered approach. We start with Layer 1, shown in this flowchart, Retrieval Augmented Generation, or RAG. This stops the model from answering queries using only its static internal memory. Instead, when a user submits a query, the system first routes that request to a vector database containing your verified external knowledge. It retrieves the factual data and places it into the context window before generation begins. You can then mandate that the model provide word-for-word citations from that specific retrieved text to substantiate every factual claim it makes. Standard text retrieval isn't perfect for every task. For highly precise relationships or complex statistical aggregations, GraphRag utilizes knowledge graphs to map exact connections that standard vector searches miss. And for absolute deterministic facts, like checking live inventory or current pricing, the model should be configured to directly call an API rather than attempting to recall data probabilistically. RAG anchors probabilistic text generation in verified real-world data at the exact moment the user asks a question. Layer 2 is advanced prompt engineering. Looking at this side-by-side comparison, a standard request on the left leaves room for ambiguity. The engineered prompt on the right acts as a structural nudge, guiding the model towards strict logic. This utilizes chain-of-thought prompting. By explicitly instructing the model to think step by step before delivering a final answer, you force the system to evaluate its own logic and catch errors mid-process. It also employs few-shot prompting. You provide the model with a few examples of correct question and answer pairs within the prompt, specifically including examples where the correct expected answer is "I don't know." You combine this with negative constraints. These are explicit, hard rules written into the prompt, such as only use the provided text, which forbid the model from guessing when data is missing. Prompt engineering functions as the primary behavioral constraint, defining the logical boundaries of the model's generation process before it begins creating text. Layer 3 moves deeper, addressing the foundational model level. These are interventions made directly to the model's training and configuration to prioritize facts over fluency. During training, engineers use reinforcement learning from human feedback. To fight hallucinations, this process must be shifted to prioritize the honest aspect of the helpfulness, honest, and harmless framework over pure conversational helpfulness. This specific alignment teaches the model that it is acceptable, and in fact rewarded, to refuse an answer entirely rather than hallucinating facts to please the user. For highly specialized technical fields, domain-specific fine-tuning further aligns the model. Training it on a curated, high-quality dataset embeds factual truth directly into the system's weights. At configuration time, we adjust the model's temperature. As this dial turns down from 1.0 to 0.1, the model becomes less creative and highly deterministic, severely restricting its ability to invent false information. While tuning and configuration lower the baseline probability of a hallucination, they are not completely foolproof. They must be paired with external, active guardrails. That brings us to layer 4, the runtime safety net. This flowchart maps out the verification mechanisms designed to intercept misleading outputs before they reach the user. The first stage is multi-agent validation. After the primary generator LLM creates a response, a second specialized LLM as a judge acts as a critic. It cross-checks the generated answer directly against the source documents to verify accuracy. The next stage introduces neurosymbolic AI as the ultimate automated guardrail. Neurosymbolic systems combine neural network perception with hard-coded logic rules. They validate the text outputs against strict symbolic knowledge graphs, ensuring the AI cannot generate an output that violates established logical facts. In high-stakes environments such as legal analysis or medical diagnostics, these automated systems operate alongside a mandatory human-in-the-loop review. An expert validates the final output. Guardrails act as the definitive safety net. They catch the complex, ungrounded edge cases that manage to slip past prompting and retrieval strategies. Eliminating hallucinations requires a unified product architecture rather than a single setting. These layers work in concert. External grounding provides the facts. Prompting sets the behavioral rules. Tuning reduces creative deviation. And guardrails independently verify the final output. This defense-in-depth approach provides the necessary reliability for deploying LLMs within production-level enterprise environments. Hallucination mitigation is one critical module in the broader landscape of AI product management. It sits alongside disciplines like agentic architecture, discovery, and lifecycle KPIs. To stop building fragile AI and start architecting robust product strategies, subscribe to the AI Product Management Playbook by Deepak Deo. Join our network of product leaders today.